Welcome to today's episode of the Chem OG. Our topic today is atomic size. The size of an atom can tell us some broad properties about the reactivity of that particular atom. So what are we looking for when we talk about atomic size, or sometimes what's called atomic radius? Well, as you can tell from the moniker radius, essentially this is the classical sense of treating an atom as a sphere. And the size of the atom is the average distance between the nucleus, which is the center of that sphere, and the outermost electron, which is the outer portion, or the rind of an orange, so to speak, the outermost electron. And so electrons can be drawn to an atom or can be tempted to leave based on the proximity to the nucleus. Now, plainly and simply, electrons are there inside an atom for one purpose and one purpose only, and that is because they are attracted to the positive charge of the protons on the nucleus. If the electrons are no longer attracted, the electrons are totally going to leave. Simple as that. And so the only reason that electrons are hanging out around the atom is because they're attracted to the protons on the nucleus. So if there's a strong attraction to the nucleus, those electrons are most likely going to stay. If there's a meager attraction or a weak attraction to the nucleus, then there's a chance that those electrons may leave. So smaller atoms, by definition, are ones in which the electrons are close to the nucleus. That's the reason that we're saying that they're small. And because those electrons are close to the nucleus, they're closer to the thing that's attracting them. Large atoms are ones whose outer electrons are a lot farther away. And because those outer electrons are a lot farther away, those are the ones that are going to be more tempted to leave. And so small atoms are going to hold on to their electrons more tightly. And that means that they're also potentially going to be a place that can attract new electrons, right? I mean, think about like a part of the country that's really, really attractive to stay. Maybe it's got, a really good urban environment. Maybe there's, all types of diverse restaurants you can go to. Maybe it's close to the ocean or the sea. So if there's a particular destination or a city that's got a lot of attractive things going on, chances are it's going to attract more people to come in and visit that city. And so if you have a small atom, electrons are close to the nucleus. And that is the attractive thing, or that is the main reason that you go as an electron to hang out around the atom. And so small atoms can potentially attract new electrons only if there's space available. Large atoms, on the other hand, because the electrons are so far away from the nucleus, those electrons are not tightly held. And because they're not tightly held, those electrons are more likely to leave instead. So smaller atoms can attract electrons, whereas large atoms, those are the ones that are more likely to lose electron density. So how can you tell if an atom is large or an atom is small? Well, the answer lies in the periodic table. I mean, you could look things up, in a reference source, whether it's PubChem or Wikipedia or something like that. But if you wanted to take a look at broad strokes of which atoms are small and which atoms are large, we're going to take a look at the periodic table. And as we take a look at the periodic table, I've labeled this periodic table with a whole bunch of letters. Okay, so I've labeled this periodic table with a whole bunch of letters. Now, the reason I labeled the periodic table with a whole bunch of letters is because each of these letters indicates a particular property about an atom that is large, relatively speaking. And so if you take a look at those letters and the way that I wrote them up, if you read from top left down to bottom left in a clockwise direction, right, kind of going based on the arrow that we got going on there, that spells B-E-A-N-S. Spells beans if we're looking at it clockwise starting from the top left. So if you label sort of the periodic table with those letters, what do each of those letters mean? Well, A stands for the region with the highest acidity. And in fact, the atoms that are most acidic when they have a proton attached to them exist towards the right and towards the bottom. Okay, so that's why I have that letter A towards the right and to the bottom. And that's because that's the region of highest acidity. And in particular, the type of acidity I'm talking about is the ability to donate protons. If we're looking at, instead of acidity, if we're looking at basicity, understandably basicity is going to be strongest towards the top and to the left, right? It's the opposite trend from that of acidity. And again, we're talking about the ability to be able to accept protons. So we're talking about what's known as Bronsted-Lowry acidity and basicity with respect to donating and accepting protons. The letter E stands for electronegativity, or the other periodic trend that has the letter E in it, and that is ionization energy. N stands for nucleophilicity, and S stands for size. So this is a way that you can be able to memorize all of your periodic trends in one fell swoop. Just label your periodic table B, E, A, and S, going clockwise from top left to bottom left, and there you have all your periodic trends all at once. And the one that we're talking about today is that trend for size. So that trend for size is the one that we're discussing right now. And so the atoms that are largest then, based on what we just wrote, are the ones that are to the bottom and to the left. Or another way of saying the same thing is that atoms that are smallest are going to be towards the top, and they're going to be towards the right. Okay, so this is the region right here where atoms that are very, very small exist, and this is the region right here in which atoms that are actually rather large, exist instead. And so if I take a look at any given row in the periodic table, so let's say I take a look at the second row in the periodic table. It's the one that begins with lithium, and as we move across from left to right, it ends with neon. The smallest element in that row is actually neon. The largest element in that row is lithium, right? That's no different from what it is that I'm saying, with size increasing towards the bottom and to the left. So if I take a look at any given row in the periodic table, the largest element is always going to be the group 1 metal. So sodium is the largest element in this row, potassium is the largest element in the 4th row, and so on. And the smallest element is always going to be the noble gas. So krypton is much smaller than potassium. Argon is much smaller than sodium, and so on and so forth. So if we're looking for smallest size, look towards the noble gases. If we're looking for largest size, you want to look towards the group 1 and group 2 metals instead. So now that we know that we can determine relative size from the periodic table, again, let's go back to the conclusions that we can make. So smaller atoms are towards the top and to the right, and if there's space available for an extra electron, those small atoms readily attract electron density, and they can also better stabilize negative charge. So let's talk about that last portion. The reason that these small atoms can better stabilize negative charge is because negative charge is a problem inherently because I have too many electrons. Well, the best way to stabilize too many electrons is to have them close to the nucleus, because that's the place to which they feel that they're most attracted, right? And if you think about our analogy of talking about, destination cities or touristy cities, there's a reason that even though those touristy cities are crowded, they still, right, attract more people. It's because there's something that's attractive about that particular, city or destination. And so electrons are willing to put up with that extra repulsion if it means that they get to be close to the nucleus. And that's what we have with small atoms. And want to make a note that even though the noble gases are the smallest element in a given row, which is what we talked about a little bit earlier, the reason that they don't attract new electrons is because there's no space for that extra electron. Okay, so noble gases, as you know, have a full valence shell, and so any incoming electron can't go in that same shell. And that's the reason that those noble gases don't attract any extra electron density. But it's also that same reason that halogens, fluorine, chlorine, bromine, iodine, it's the reason that those elements are able to attract extra electron densities, because they're the second smallest element in a given row, and they do have space for an extra electron. Larger atoms, things like the group 1s and group 2s, those are atoms that lose electron density instead. And that's because they're large, the outermost electron doesn't feel that much of an attraction to the nucleus, so there's a very good chance that those electrons might be lost. And so if we're in an environment that can stabilize a positive charge, because losing an electron from a neutral atom is going to generate a positive charge, if we have an environment that can stabilize cations, we often see that those group 1 and group 2 metals are going to be forming positive charge instead, because they're large and the electrons can't wait to leave. And so the size of an atom, for summarizing here, generally affects how it reacts. Smaller atoms are more capable generally of attracting electrons, and electrons are more likely to leave a large atom instead. And size is big picture
one of the factors that can help stabilize molecules. So this is a mnemonic that I've mentioned repeatedly, and that is RAISE, R-A-I-S-E. Tonight we talked about the S in RAISE, but here are all of them together. And if you're interested, please check out the other videos that speak about the other stabilizers. So good luck studying. Hope you learned something from today's lesson. I'll see you at the next one. Don't forget to like and subscribe.